So, in this course on testing and verification, as you are aware that there are going to be two different tracks. One track is the one which has already started in the last week, namely the track on testing, and this is the other track which is on verification. So, I will be teaching the track on verification and Professor ISG will be teaching the track on testing. So, today I am going to give you an overview of what verification means and what are the major challenges that are faced in the verification community. So, within the verification group that we have in the institute, we work not only on hardware verification, but on a variety of other types of verification like verification of automotive systems, verification of web interfaces and software verification. Hardware verification is one of the areas in which we work, and this course is focused on hardware verification. Okay. I intend to cover mostly digital design verification, but towards the end, if time permits, I am going to talk a little bit about the analog and mixed signal verification techniques which are emerging in the verification community. So, it is going to be mostly sort of industry friendly kind of course, because it is something which has been applied is being applied and is being regularly used in the industry. So, we are going to catch up with some of the technologies that are there today. So, the main reference books that I will be using is, the first one is Hardware Design Verification, Simulation and Formal Method Based Approaches by William Lamb. This is this book that I have here in front of me, and then and I will also teach the formal methods part mostly from a book which I wrote a couple of years ago. This is a roadmap for formal property verification, and from Springer. So, the second book, the one that I have, for that it is available in the e-books of Springer, and the institute has e-books subscription. So, you should be able to download the book from the Springer website. The course slides and all the resources related to the verification track will be put up in this course web, which is facweb.iitkgp.earnet.in/Pallab, and then you follow the links to the courses. Okay. So, to start with, let us look at the complete flow through which a chip is designed, from the concept to the final productization of the chip in the market. So, broadly there are four major steps. The first step is the specification. This is where we specify what we want to design, all right, and this is a step in which there is a lot of deliberations made by engineers to decide that exactly what are the features that has to be implemented on the hardware circuit. The second phase is the implementation. Now, this implementation is not the actual product that is implemented, but it is the development of the design in a symbolic language, right. So, that is called the implementation. So, this is still pre-silicon. What we mean by pre-silicon is that at that point of time you are still working on the computer, you do not actually have the chip, okay. There is no silicon that you have created, and then the later part is post-silicon. So, post-silicon is the point of time when you have started fabricating the chip. So, under this, typically there are two steps that are taken. One is prototyping, where you get a first prototype of the chip developed, and then you have the final manufacturing, where thousands of copies of the same chip are taped out, all right. Now, the gamut of verification is in the first three, and the gamut of testing is in the second two. Now, what do we mean by verification? We want to see whether what we wanted to design, whether that is correct, in the sense that we are not trying to design something which we cannot design, okay. So, what we want to design, the specification, has to be a feasible one. So, that is part of the consistency analysis, the satisfiability of the specification. That is one part where you verify whether the specification itself is correct. The next step is checking whether the specification has been correctly implemented. Whatever we have implemented, is that what the specification demanded. So, that is the second step of verification. And then the third step, when we have the prototype, we still do a verification, because we want to make sure that whatever prototype we have developed, is that correctly implementing the design intent. All right. Now, this step, this prototyping step is there for a multitude of reasons. One of them being that all the verification that you do pre-silicon has to be done through simulation or symbolic methods, and they are computationally expensive. On the other hand, when you have a first silicon available to you, then you can actually run that with an actual clock, and it is going to run much faster than you would be able to check it in the pre-silicon, right. So, that is why a lot of prototyping and hardware emulation is done, and that is also part of the design validation, because it may still point out errors in the design itself, the logic of the design itself. And then what does actual testing do? The testing is not to find out whether the design is correct. Rather, when we actually translate a valid design into the circuit, there is a possibility that the circuit, because of the manufacturing process, may have defects, right. So, we are not verifying the logic of the design anymore. Rather, given the logic of the design, we are trying to figure out whether the chip actually is having the same logic or not, or by virtue of certain faults has the logic changed in the final chip. Okay, that is what we want to test. Now, there you see it is a structure based approach. We are not dealing with functionality anymore. Functionality, the logic, the gates that we need, they are already decided, frozen and agreed upon. What we are trying to see is take the gates, the connections between the gates, and see whether that has been properly translated into the final silicon, right. So, that is why you will see that in the testing phase, your reference is the design, and you have a fault model, and you take the fault model and the reference design and try to generate tests that will check whether each path in that design has been properly implemented, or if there is a fault in that path, whether it propagates to the output and shows you some deviation from the expected output. Alright, that is testing. In verification, you do not have that reference, because your design itself is in doubt. You are not sure whether the design is correct, right. So, that is why the specification is important, because that is the reference for verifying the implementation. So, there are again another set of problems, that what if the specification itself is incorrect, alright. So, the specification could be incorrect and the implementation could be correct, or the specification is correct, the implementation is incorrect, and we have to debug and find out which is actually the case, alright. So, this is broadly to put in perspective what is verification and what is testing. So, this slide shows you the design and verification steps. So, you start with the specification here, and the design, by design we mean that it is the set of steps that you take from the specification to the implementation. That is what we mean by the verb design. Okay. And the verification task is that given the implementation and given the specification, you want to check whether they are actually doing the same thing, whether my implementation is satisfying the design intent, alright. That is the verification problem. Let us look at some of the design challenges that are there today, because design and verification are very closely related. Whatever are your design challenges, whether you are able to meet those challenges is the equivalent verification problem, right. So, suppose we have to design a pacemaker chip. Suppose we want to design a chip which is going to be used in a pacemaker, which will be implanted in a human being. So, the core challenges are like this. First thing is, we have to minimize the delay. What is the delay? Every circuit has a delay, the delay that a signal takes to propagate from the input of that circuit to the output of the circuit. All right. Now, we have to keep the delay to the minimum. Why? Because we want to make sure that you are able to produce all the pulses within the right time. You cannot delay that, right. Now, as you have the delay optimization problem, in parallel to that, in the verification side, you will have the timing analysis problem. Given a circuit, find out what is the critical delay of that circuit. In other words, how much time does it take in the worst case for a signal to propagate from the input to some output. All right. So, that is a critical delay analysis, and then that has to be done accurately before you actually tape out the chip, right. So, you have to have good models for the delay times of the gates, and that, as you know, being a circuit, is going to change from technology to technology, depending on the dimensions of the transistors that you are synthesizing. The delay will vary, right. So, before you have the silicon, if you have to do this timing analysis, you need very good models for the time and the time that it takes to propagate from one input of a gate to the output of the gate, right. Next step is that we want to minimize area, right. We do not want to implant a huge device under the skin of the patient, right. It has to be very small. Now, you know, area and delay are conflicting criteria, right. If you want to reduce one, the other one goes up, right. Now, you may be aware that there are technologies which are faster than CMOS, but they are not so popular. Why? Because they are not good in terms of area. They are not good in terms of area, they are not good in terms of power. So, CMOS is good in those. So, that is why you get better integration, and with less power you can operate that. Now, area optimization is a problem, and corresponding to that, you again have on the verification side that the problems relating to, you know, how have I put all the I have to pack all these transistors into a very small amount of area, and there are rules for doing that. I cannot pack them in arbitrary ways, because if I pack them in arbitrary ways, what is going to happen is there will be a lot of parasitic capacitances and inductances that will come between the different the polysilicon, the metal, and between metals, etc., right. So, in the verification side, we have to make sure that when we integrate this thing, we are not violating any of those rules, right. And to give you an indication of, you know, what kind of challenges people are facing in terms of this, in delay and in area, there is a new technology which is coming up, in which I was hearing a lecture by the president of TI India, Dr. Bobby Mitro, when he visited here last time. They are building a technology by which a blind person will be able to see. Now, how are they going to do that? They are going to have a small camera sitting in the place where you have your retina. It will capture all the images and then generate on the optic nerve exactly the kind of electrical impulses as your eyeball does to the optic nerve. So, what is going to happen is that the blind person is going to get the same impulses as a normal person, and will be able to see that thing. It is not going to be continuous motion as we see, but at least it is a big step, right, for a blind person. Even if he can see in frames, snapshots, still that is a great thing to have. So, now you can imagine that if you have to do all those image processing and then producing the impulses, etc., and you want to implant that in a space as small as the eye, So you need really good optimization of the speed by which you process all this and the space required to implant that. The next important criteria, and probably the most important criteria in today's generation, is to minimize power. Why power? In the context of a pacemaker, it is very important because it is battery driven and batteries have limited life, and it is an implant. We do not want the patient to go through that operation once every year, right. So, we want to have batteries which are going to last preferably his entire lifetime, right. Now, battery technology is not coming up that fast. They are improving a lot, no doubt, but not to the extent that you can design whatever circuit you like and then expect the battery to last that long. So, power management within the circuit is a very important criteria. How do you manage the power in your circuit so that you are not wasting any power? And believe me, in most circuits which are not optimized for power, there is a colossal waste of power, because at the same time you are not using all parts of the application. Think of your cell phone. Your cell phone has many different types of circuits. Okay, some of that is producing sounds for you, some of that is you may have an FM radio somewhere inside it, you can have a Bluetooth connection, you can have a Wi-Fi connection, then you have the standard phone connection, GSM or CDMA, and then there is a host of other applications which run on cell phones today. You are not using all of that all of the time, right. So, the system has to be intelligent enough to switch off powers or reduce to low power states all those portions of the application which are not being used at this point of time. So, that is a challenge both in terms of the hardware, how do we design the hardware so that we can do this power management, and it is also a software challenge, because previously we never thought about power when writing software, but now it has to be optimized for that, right. You have to know that the more of computation that you do, the more power you are eating up, and you have to distribute your application in such a way that it is working on individual power islands and not keeping the whole circuit alive all the time, right. So, power optimization is an interesting thing, and the corresponding verification problem is to make sure that you are not exceeding your power budget at any point of time. So, there are new specification languages like UPF and CPF which are used to specify the power intent of a chip. Okay. These are new standards that have come up. The next thing is to improve the verifiability. See, we have gone from chips which had a few gates to a few thousands of gates to a few millions of gates to a few billions of gates, and we are still growing. Now, what is happening is that the amount of time that is spent in verification of these designs is growing exponentially, because most of the verification problems are not tractable problems. They are not in P, they are harder problems, NP complete and harder. So, the larger your size becomes, the complexity will grow exponentially, and today more than 70% of the total time in designing a chip is spent in verification, right. So, it is very important to make the chip verifiable. So, this is I am taking also the PDS course this semester. So, the first thing that I told students is that when you write a program, you are not writing the program for yourself, you are almost always writing it for someone else, right. So, it is very challenging, intellectually challenging to write a program which no one else can read, but you will never get any appreciation for that, right, because it has to be a program which others can read. And in any case, eventually the compiler has become so intelligent that it is going to take the naive program and the well optimized program and produce an executable which is almost the same, right. So, all the effort that you do in writing an absolutely unreadable program goes to waste. So that is the same case in designs also. Okay. It has become very important even at the cost of the lower things that we said here, that is area and delay. People are trying to build designs which are reusable, which are verifiable, easily integratable with other designs, because that is what is where it is beginning to pinch. See, we want to reduce that 70% of the time and not improve the 30% of the time, right. So that makes sense. So that is why improving verifiability, reliability and coverage is a very important thing. Then the reliability aspect. This reliability is different from the previous verifiability. Verifiability is to check whether it is functionally correct, but reliability is about its correct implementation in silicon. Why is that becoming a major issue? Because you are going down in technology, so you may be knowing that the dimensions of the transistor is shrinking with every new technology that we are having. So the fab support that we have here for digital designs is 180 nanometer, 0.18 micron. The support that we enjoy from National Semiconductors in our lab is 0.18 micron. Now from that, today there is a lot of designs which are done in 45 nanometer, and next we are going into 32 nanometer, right, and there is no sign that it is going to stop there, right. So there is a law called Moore's law which says that the number of transistors doubles every 18 months on the same area, right. So people thought that that law would not survive, but then we are having Moore's law, more of Moore's law, more of Moore's law, and there is no sign of slowing down. Now what is happening as a result of that is that the transistors do not look like transistors anymore if you see it through a microscope, because it has become so small that all the boundaries of the regions of the transistor have become very irregular now, because you cannot reliably put all your atoms and molecules in the proper places when you are working at that kind of miniaturization. And as a result, what is happening is that many of those are becoming defective. So while on the one hand we have very small transistor geometries, on the other hand many of that is not being correctly fabbed. So that is what is in the parlance of design, it is called as low yield, right. The yield is low. So you have to design knowing that the yield is going to be low. So you have to do things like replicating transistors, replicating parts of the design so that reliability improves, right. So it is not just one optimized design anymore. You need to have redundancy in many places wherever you feel that the yield is going to be low, right. Then testability. So when you had only 5 gates in your chip, it was easy to test the chip, right. You just drive all possible inputs and see how it works. When you have a few trillion gates in your chips, then testing that chip is a nightmare, right. So how are we going to improve testability? More so because today you are going to integrate cores from different vendors into your chip. They are all similar looking components, but how do you test all of them? So for example, in a typical router chip you can have something like 200 processors on one chip, right. Now it may be a replica of the same processor, but you still have to make sure that all 200 of them have been correctly fabricated. From a design point of view, you verify one of them, you have verified all of them. From a testing point of view, you have to test all 200 of them, right. So how do you actually get access to the internals of this chip? So that is what you are going to learn in the testing track, so I will not dwell too much on that, but it is another major challenge. And then finally we want to reduce cost. Have you heard of anything other than transistors whose cost goes down consistently for 20 years apples, oranges, petrol, right. So, this is the only, possibly the only major technology area which has continued to deliver reduction in costs for many years, right, and we still want more. To give you another example from Dr. Bobby Mitra's talk here, they are coming up with an USG machine which is portable. USG, you know, ultrasonography. It's an expensive test. Typically, some of the upscale clinics, it's going to cost you something like 800 to 1000 rupees for getting an USG done. But they are trying to come up with a portable device which you can carry to the villages, and it's going to cost you 100 rupees to take one USG done. And they are trying to bring that down to something like 10 rupees. Right? Now, that is where technology will start impacting lot of people, like the cell phone has done. Cell phone has become affordable, costs have gone down. Nothing has penetrated the Indian rural areas more than the cell phone. Right? So, the next thing is whether we can take medical electronics to a level where this kind of penetration can happen in third world countries which cannot afford state of the art medical facilities. Right? So, it is a big challenge, and it is a challenge which does not seem very unrealistic anymore. Right? So, it is very exciting. There is a center, you may be aware of medical electronics funded by Texas Instruments, which is coming up in the institute. So, it is a new facility. So, it is interesting to see that how does this impact the computational problems, because bottom line is, we as computer scientists, as scientists, we have to look at the computational aspects of this verification. How do we actually map it into symbolic formalisms and then solve them. So, if you look at the earlier parts of the 80s, when we were in school, and most of you were not born. So, at that time a lot of designs used to be done just using transistors. Today digital designs are almost never done at this level, but analog designs are still done at the transistor level, because analog designs are not, they are not as large as the digital designs, though probably much more complicated. So, this level we call it as schematic. Okay. Then when the transistor level designs started becoming too complicated, we raised the level of abstraction. We said that we can't specify everything at the transistor level anymore. Let us use gates to specify the design, gates and flip flops, and the corresponding formalism is Boolean logic. The reasoning is based on Boolean algebra, and for the states we have finite state machines. Right? So, this is the formalism. So, in this region there are a lot of computational problems, like how do you minimize a state machine, how do you encode a state machine. You have studied all this in your switching circuits and automata theory course, right. So, then when gate level designs became very complicated or too large to handle, we raised the level of abstraction even further. So, we said let us do a design in the transistor level or register transfer level, where we have registers and you have the usual Boolean logic, right. So, this is a typical code at the register transfer level. We are going to talk about this in more details later on. So, what is the formalism that we have there? We started introducing restricted semantics of programming languages, and not only just programming languages. So, you have things like if then else, you have for loops, etc. in the language, but we also have communication between concurrent state machines. So, you have synchronization, like always at passage clock, which means that this is going to get triggered whenever there is a positive edge of the clock, right. So, you can have, instead of passage clock, passage of A, where A is a signal which is driven from another block, right. So, by virtue of that you can have synchronization between concurrent systems, and there are more you can have sharing of variables between these systems. One is the output of one and the input of more than one of these blocks, right. So, the formalism there is not just one finite state machine, but a set of communicating concurrent finite state machines, right, and the language support is much higher in terms of the level of abstraction as compared to Boolean logic or finite state machines. Now, today even this is going to be very large. So, I will show you some codes from, say for example, I will show you the code of the SunSpark processor, which is one of the state of the art processors. So, you will see that it has become huge, millions of lines of code for one design. Now, that again has become very it is very difficult to navigate that. So, we need to raise the level of abstraction even further. Now, raising it even further has the following problem, which is very important to understand. There is one thing which binds all of these, and that is logical equivalence. See, whether you specify here or here, the bottom line is it exactly specifies a digital circuit. What is a digital circuit? It is a finite state machine, right. The bottom line of all of these is that it implements a finite state machine. So, the finite state machine that you get out of this and the finite state machine that you get at this level, they have to be logically equivalent, right. But what are we going to do above that? We are reaching the limit in which the specification of the logic itself has become huge. The logic itself is huge. If we raise it further, then we cannot preserve the logical equivalence anymore. So, this is a very important understanding. So, when we are raising it further, we are saying that the specification that we are building is not an exact logic for the implementation, rather it defines certain properties that the implementation has to satisfy. What does that mean? That means that for the same specification you can now have many different implementations which are not logically equivalent, right. That is not a bad thing to happen, because it gives you room for optimization. If for the same specification you have 20 different implementations, then you can talk about which is the better of the 20 in terms of certain performance criteria, and you can decide to choose that one. And then you can have tools which are going to search that space and come up with the best design, right. That is what we mean by optimization. So, if the specification was very tight and would give you only one implementation, then there is no scope for optimization. You will just have a rule of thumb implementation for that, and there is no room for optimization. So, there is a gap between the specification and the implementation, and that gap represents the gap within which we do design space exploration and come up with the optimized design. Okay. Let us go through an example quickly to give you a flavor of what we want to do. Okay. This is a very simple toy example. We want to design a 2-bit gray counter. What is a gray counter? It is a counter which is going to count. So, 2-bit means how many values, how many states can it have? 4 states, right. And these states should be such that successive states will differ only in 1 bit, right. So, how is can you give me one way of doing that? 0 0 0 1 1 1 then 1 0 and then back to 0 0. So, if you look at this sequence, then every successive state differs in exactly 1 bit. So, in addition to that, this counter has a reset, and whenever the reset signal is raised, then the counter returns to the value 0 0. Okay. So, this is a state machine representation of that, where you can see from 0 0, when we get a reset it stays in 0 0. If we do not get a reset, it goes to 0 1. If we do not get a reset, it goes to 1 1. If we do not get a reset, it goes to 1 0 and then back to 0 0. So these blue arcs, if you can make out the difference between the blue and black ones, the blue arcs are the ones which is normally taken when the counter is running, and the black ones are the ones which are invoked when the reset is high and it returns the machine to the initial state of 0 0. Okay. So now given this state machine, we can construct a state transition table. Okay. So this state transition table has these entries: the present state, the input and the next state. So if the present state is 0 0 and the input is reset is 0, then the next state is 0 1, because the reset is low. So we go from 0 0 to 0 1. Okay. Similarly, when we are in 0 1, if the reset is low, we go to 1 1. So 0 1, reset is low, we go to 1 1. Right. On the other hand, when we are in 0 1, if we have reset, we will return to 0 0. So when we are in 0 1, if we have reset is high, we will return to 0 0. Okay. So this is the state transition table. Now we can read the state transition table and create what is called the state transition functions. So let us look at one of these. So n0. So if you look at this table, where does n0 become high? In this entry, okay, this is where it is high, and then in this entry, this here again it is high. Okay. So we can read off these two entries and say that when S0 dash S1 RST dash, okay, or R dash, S0 dash S1 R dash, this term, right, this term here, and then when we have S0 S1 and R dash, S0 S1 and R dash, in these two cases N0 is 1. Is that clear? And similarly N1 is 1 when we have in this entry and in this entry, right. So again S0 dash S1 dash R dash and S0 dash S1 R dash, right. So these two represent the state transition functions, and the state machine that we saw in the last slide is exactly represented by this set of state transition functions. All right. Then we can minimize the logic of the state transition functions, and then you can see that this N0 can equivalently be written as S1 R dash, all right, because you can take S1 R dash common here, and then what you have is S0 plus S0 dash, which is 1. And similarly N1 can be minimized to S0 dash R dash. Now given the state transition functions, we can write a Verilog code at the register transfer level as follows, which says that gray counter is a module which has S0 S1 and reset, is input RST is an input, and S0 and S1 are registers. Okay. Always at passage clock. So whenever there is a positive edge of the clock, this is what we are going to do. We are going to assign S0 to S1 and not RST. Now see, this is this function. We assign to S0. Now remember that it is the same register. So N0 and the NIs and the SIs are going to be stored in the same register, only after one clock cycle. So S0 is going to be assigned S1 and not RST, this one, and S1 will be assigned not S0 and not RST. Okay. And there is something about this less than equal to. It is called a non-blocking assignment statement. Okay. We are going to talk a little bit about this later on. What it means is that this is going to get executed using the previous value of S0 and S1. Right. So after that is done, then again it is going to wait for the next clock cycle. So, in every clock cycle this is what is going to happen, right. Now, when you have this Verilog code, if you write this Verilog code like this, then the tool, the synthesis tool, will take this as the input and actually produce the circuit that is to be finally implemented. All right. So, the design is entered at this level and is output by the CAD tools at the circuit level. So, it can produce it at the gate level, at the transistor level, okay. And finally, when you have actually completely laid it out, it is going to produce what is called the GDS2 format, which is then directly goes into the fabrication system, okay. So, to summarize what we have talked about here today is that there are various abstractions in the design flow. So, in this picture, the higher up that we are, it is a higher level of abstraction. The lower down that we go, it is a lower level of abstraction. And the higher up that you have, the less details that you have, and the lower you go in the abstraction level, you add more and more details. So, we start with the functional specification, which is at the top level where you specify what you want to design. Typically, this is done as an English language document. For processors, the chip design companies like Intel, IBM, they call this as the micro architectural specification. And there is a very coveted group of people called micro architects who are responsible for designing the architecture, and this actually talks about that architecture level specification. And believe me that they are very important people, because of the technological advances, the synthesis process, the process of translating the design from the implementation to the final chip, has become standardized has become mostly standardized, and there are very good tools available. And the room for optimization there is not very much, because you see it is the same set of tools which are being used by many companies. So, all the innovation and the IP takes place at the architecture level. That is where you decide how many processor cores are you going to put on the chip, how are you going to fetch the instructions, how are you going to pipeline them through your processor, how many registers are you going to have, what are the instruction sets that you are going to support, what are the addressing modes you are going to support, how are you going to manage the cache, how will you manage cache contention between more than one core which is running on the same processor chip, right. So, all these issues are architectural issues, and that is where most of the innovations are coming in. So, you can imagine that that is what the microarchitects do and document in terms of the microarchitectural specification. It is very important that the designer understands what is needed there, right. Otherwise, that is going to remain as a story, and the final chip which is going to come out is going to do something else, right. So, the next step is the algorithmic description. This is where you start defining the way you are going to implement that microarchitecture, okay. And people develop high level models for this. These high level models could be written in languages like C, C++, or in languages like System C or Spec C or BlueSpec Verilog. There are lots of new languages in this space, and then it could also be in something a little bit lower down like System Verilog. At that level, these models are first verified. So, you check whether the model is actually properly implementing the microarchitectural specification, right. So, this is the algorithmic level analysis. When you are sure that this is all right, then you start writing the RTL. Now, the interesting thing is that today mostly the arrow that you see here between algorithmic description to RTL is manual. So, after all doing all that modeling, etc., all that you have done is you have checked whether your implementation is implementable, whether your architecture is implementable. but then you start writing the RTL code again by hand, right? And that again is a source of bugs, because the RTL designer may not now interpret the architectural specifications in the correct way, right? There is a lot of development going on to make this step automatic, whether we can go from the algorithmic description to the RTL in an automatic way, okay? But it's going to take a lot of time before we reach there. Then thereafter these steps are well automated. From RTL you synthesize to a gate level netlist, then you synthesize that into a transistor level netlist, and then finally it is physically laid out on the chip. All the polysilicon, the metals, everything is laid down on the chip. That is the physical layout, right? And finally it goes into tape out. All right. So these are the steps that take place in the abstractions in the design flow. From a verification perspective, it is very important, because for each level of abstraction, the verification that you can do at that abstraction level is going to vary. All right. So in the next lecture, I will complete this section on introduction, and then we are going to look at more of the verification aspects of this. Thank you.